Hello, welcome to IB Physics. My name is Mr. Tompkins, and this is Unit 5, which is electricity. We're going to start off with Lesson 1, which is going to be electric charges. Now, before we start talking about charges, let's start talking about exactly what is electricity. Electricity is just the movement of these electric charges, which we'll talk about here in a little bit. And it's either through air, which in this case would be lightning, or more commonly through wires in our houses or businesses or places that we frequent. Any place that has electricity usually has wires. So let's talk about what is charge. A charge is just a physical property of matter that causes it to experience a force when it's placed inside of an electromagnetic field. So it's a property of matter. And there are two types of charges, or two charges that matter can have. The first one is a positive charge, and this is located inside that object's or particle's protons. So we start talking about protons. Protons have a positive charge. So if we have an object that has a positive net charge, that means it has more protons than it has negative charges, which is electrons. So your book likes to use the term plus sign with VE, and I'm assuming that it gets the VE from the last two of positive and negative. So you have a positive and you have a negative charge. Negative charges live in the electrons, and positive charges live in the protons. If I were to look at an atom, and so let's look at a hydrogen atom, it has one electron and one proton, and the electron circles around the proton. And this is kind of the basic model of an atom. Well, we have one negative charge out here, and we have one positive charge in the middle, and these two negative and positive cancel out, and you have what's called a neutral charge. So the charges are neutral, usually in nature. Now, what we can do sometimes is we can pull these electrons off, and that's what electricity is. Now, charges are measured in coulombs, which is given by a capital C. And so if you see a capital C, it means coulombs, which is just the measurement of charges. Variable for charge is a capital Q, or sometimes you'll see a lowercase q, and I'll explain why later. An electron or a proton, they both have the same amount of charge, and it's 1.602 times 10 to the negative 19 coulombs, which also equals this little e. So anytime you see this little e, it means that the object has this much charge, the same amount of charge as an electron. And so if I look at this, then this has a positive e. The proton here in the center of my hydrogen atom has a positive e, and the electron has a negative e. And so once again, they cancel out because they each have the same amount of charge. One is positive and one is negative. If I were to look at carbon, carbon has 6 protons. So if I were to pull all 6 of the electrons off, then it would have a charge of 6e. If I were to look at just those 6 electrons, then that would be negative 6e. So this would be all the protons, and this would be all the electrons, and then they cancel out. Now, charges behave very predictable whenever we put them next to each other. If I have like charges, or two positive charges next to each other, they will repel. They will want to push each other away. And then likewise, if I have two negative charges next to each other, well, then they want to repel each other also. The only time they start doing anything else besides repelling is whenever you put them close to each other, both positive and negative, and opposite charges, they attract each other. Now, you've seen this kind of phenomenon before, where we take a Van de Graaff generator, we place our hands on it, and next thing you know, you end up with this really amazing afro. Now, what it is you have electrons that are being stripped off of your hair, and it goes through the Van de Graaff generator, and what you're left with is a positive charge on each positive charges on your hair. Now, all these positive charges, well, they really add up. And so the positive charge on this hair is actually repelled by the positive charge on this hair. And it's also repelled by the positive charge on that hair. And next thing you know, you have this really amazing hairdo because all of the positive charges inside the hair are being pushed against each other, and they're repelling each other. Okay, so let's talk about the electric field. The electric field is a region of space where a charged particle will fill an electric force. So whenever we see a charged particle, we know it's charged. If we place it into this field, it will fill a force. And the direction of the electric field, it is a vector, is determined by what would happen if we put a small positive charge in that field. So what would happen to that small positive charge? So, well, if I were to place a small positive charge here into my positive charge area, Well, these are like charges now, and so it's going to repel. All right, so anytime that I put a small positive charge next to a positive charge, it's going to repel. And so the electric field around a positively charged particle is always going to point out. Okay, and then likewise, if I were to place a positive charge over here, well, it's going to point, it's going to be attracted to the negative charge. And so anytime that I have an electric field around a negative charge, it will always point towards that negative charge. And so if I have a positive charge or a negative charge by itself, it's easy to predict what direction the electric field will be pointing and what direction a charge will be moving. Now, if I have them close together, so let's say I have a positive and a negative close together, these are what's called a dipole. And if I were to place a positive charge here in the center, well, it would be repelled by the positive charge, but it'll also be attracted by the negative charge. So it will, in essence, move to the negative charge still. So it's going to move in this direction. So it's going to leave the positive charge and travel to the negative charge. Now, if I were to place it up here, it would actually follow something like this. It would be repelled in that direction from the positive charge, but then it would be attracted down, and so you would get an electric field line that looked like this. And as a matter of fact, in this case, they will always go out and in. And it should be somewhat symmetrical. I'm just not very good at drawing. But it would go something like this. There we go. So that would be the electric field of a dipole. Now, if we were to take all of our charges and line them up in rows, well, we get what's called a uniform electric field. Now, on the edge here, these would still have the dipole kind of effect, where we have curved. But if we make this long enough, then we could get a perfectly uniform electric field in the middle here, where a proton would be, or a positive charge would be pushed through, pushed straight through. This is actually quite helpful when we go to do some experiments. But just to know that this is possible is very informational. All right, let's talk about the electric force. This is going to be the first time we're actually going to do some math. And so we have this equation where it has the force equals K times the charge of one object times the charge of another object divided by the radius squared. And K equals Coulomb's constant. And Coulomb's constant is gotten by this equation right here, which isn't that important for us right now. Just know that you just need to know that it's 9 times 10 to the 9th newtons meters squared per coulomb squared. And your book likes to use this number here, but I don't like to because, well, how many sig figs does this have? This only has one sig fig. All right, and I don't like the fact that it has one sig fig. So what we're going to do is we're going to say that that is actually 3 sig figs. So anytime we do calculations and we're going to have significant digits, make sure you use 3 significant digits on this. It's actually 8.99 times 10 to the 9th. But your book is using the 9, so I will too. All right, let's erase all this so that we can talk about what epsilon is. Now this equation, like I said, is what we use to calculate this 9 times 10 to the 9th, but it's actually 1 over 4 pi epsilon 0. And epsilon stands for the electric permittivity, right? And in a vacuum, it is gotten to be 8.854 times 10 to the negative 12 coulomb squared per Newton per meter squared. And so this is experimentally gotten. And the more conductive the material it is, the greater the electric permittivity is. Okay, so this is based on the material. Now, the capital Q is the charge of the environmental particle, and I'll explain what that is later. But I like to distinguish between the environmental particle and the particle of inquiry. And so the particle of inquiry is the particle that we're wanting to know information about, or we're wanting to solve what is the force on that particle, or what is happening to that particle. And then we have R, which is the distance between the center of the two charges. Now, it is not the distance between the surface of the charges, all right? Not that distance. It's the distance from this center to that center, all right? And that's because the electric charges can be summed up as being in the center of each of their respective particles. And so if I were to look at an equation here, or an actual example problem, we have the electric force. We have a negative 5 microcoulomb charge that's placed 20 centimeters away from a 10 microcoulomb charge. Okay, what is the force on the negative 5 microcoulomb charge, and is it repulsive or attractive? Now here's, we can go ahead and answer this repulsive or attractive right off the bat. We have a negative charge and we have a positive charge, so these are opposite charges, which means they're going to be attractive. It's going to attract. They're going to attract each other. And so if I were to look here, I know that Q equals, my lowercase q, my inquiry, is going to be, well, I put 5 microcoulombs. Because in this case, when we're talking about forces, the negative symbol isn't really going to matter a whole lot, but that should be negative 5. We can put negative 5 in there if you wanted to. But it's not going to matter because you're already going to intuitively think about the direction as being attractive or repulsive. The charge of the particle, the charge of the environmental particle is 10 microcoulombs because that's not the one we really want to know about. We want to know what is the force on the 5 microcoulombs. So if you notice on both of these, I've converted them into coulombs. All right, and micro stands for times 10 to the negative 6, and so they get converted into coulombs. Now K, we said before, was, or the Coulomb's constant is 9 times 10 to the 9th newtons meter squared per coulomb squared. And the radius is 20 centimeters or 0.20 meters. So if I pull up my equation and then I substitute in, all right, so I substitute, so I have all of this long, nasty stuff. All right, but if I look here, we've already kind of talked a little bit about doing equations with exponents. So what I'm going to do is I'm going to add the multiplication, so a 9 plus a negative 6, so that's 3 minus 6, so that's negative 3. All right, so it's going to be 10 times 10 to the negative 3 on the top. And then I can go through and multiply my beginnings. So that's 90 times 5, which is 450 times 10 to the negative 3, and then divided that by 0.20 squared. And I get the force equals 11.25 newtons. Okay, so the force between these two charges is 11.25 newtons. Okay, so let's talk about the field strength. The strength of an electric field is determined by the force experienced on a positive charge if it's placed at a point in that field. So if I were to place a positive charge here in this field, what would the field strength be? Well, it would be the force felt by this positive charge. It is a vector. Okay, just like before, it's the direction that the positive charge would move. So in this case, the positive charge would move down, and so the electric field strength points down in that direction. And its units are newtons per coulomb. So if I have 2 coulombs of charge, I can calculate that. It would just be twice the field strength. If I had a half a newton of charge or half a coulomb of charge, then it would be half of the electric field strength would be the force involved. And I'll show you how to use that equation. Here's the equation. We actually have 2 of them. The electric field strength equals the force divided by the charge of the inquiry or our inquiry particle, and or the Coulomb's constant times the charge of our environmental particle divided by the radius squared of the distance from that particle. E is constant in a uniform electric field. So it doesn't matter anywhere that I put my positive charge in a uniform electric field like this capacitor I have here. If I were to place it down here, it would still have the same electric field force or the electric field strength as up there. The reason is because it's closer to the positive here, so it has more positive force, but it's farther away from the negative, so it has less attractive force. But here it has less repulsive force, but it has more attractive force. So let's work an example. We place a 4 microcoulomb charge in a uniform field with a strength of 2 newtons per coulomb. What force will it experience? Well, so I went ahead and converted the 4 microcoulombs to 4 times 10 to the negative 6 coulombs, and we have 2 newtons per coulomb, and so I rearrange this equation. My electric field strength equals the force divided by the charge, and I get the electric field strength times the charge equals the force, and so 2 newtons per coulomb times 4 times 10 to the negative 6 coulombs, and I get the force equal to 8 times 10 to the negative 6 newtons. So it's a very small force, but that's the force that I have. Okay, because electric fields are vectors, we must add them as such. So if we have 2 electric fields affecting a certain point or a certain particle, then we have to add them together using vector notation or vector math. So if I want to know what is the electric field strength at point A, well, that's it requires me to do some trig and some additional steps. So I need to figure out, well, what is the electric field strength here at A from the 10 microcoulomb? And if I look here, These are both positive, so it's going to be repulsive, so that's why I drew my arrow there. And then I have a negative charge here and a positive charge there, and so this is going to be an attractive force, which means it's going to be an attractive electric field strength. So let's start. We need to figure out the electric field strength from both of these particles on point A. So if I look here, well, I know that the electric field strength equals K capital Q over R squared. Well, K is 9 times 10 to the 9th. Q in this case is 10 microcoulombs, which is 10 times 10 to the 6th, negative 6 coulombs, all over R, which is 0.1 squared. Now, if I do the same thing over here, I have K, which is 9 times 10 to the 9th, times my Q, which is negative 5 times 10 to the negative 6 coulombs, all over 0.05 squared. And what I end up with is the electric field strength here, due to my 10 microcoulomb positive charge, as being 9 times 10 to the 6 newtons per coulomb. And over here, I get my electric field strength of the small negative 5 microcoulomb charge of being 1.8 times 10 to the 7th newtons per coulomb. Okay, so this is my two field strength. I have this one, and I have this one. And if I look here, these are two vectors. And so if I were to do math of them, then I would add my bottom vector, and I use the head-to-tail method, and I get 1.8 times 10 to the 7th newtons per coulomb. And over here I have 9 times 10 to the 6th newtons per coulomb. And so in order to solve out what the resultant vector would be, I just need to use the Pythagorean theorem. So I get 1.8 times 10 to the 7th squared plus 9 times 10 to the 6th squared, and then I take the square root of that, and I get that the total electric field strength for that area is going to be 2.0 times 10 to the 7th, I believe. Let me check that out with my calculator real quick. Yes, 2.0 times 10 to the 7th newtons per coulomb. Okay, so that's how I would solve for that. Now, this is just like we did before. If you wanted to know the angle of the electric field at this location, you can actually use trig and solve for that, but the question only asks for the electric field strength. Okay, well, I hope that this helps you on the homework. This is the last of lesson 1. If you have any questions, please let me know.